So now we're going to have a look at goodness of fit. So goodness of fit was had a look in AS stats when we had a look at the chi-squared distribution. Goodness of fit can be used to determine if a set model can be used to predict events. We do this by finding the predicted outcomes of each event, usually finding the probability first. Then we use the goodness of fit function to determine if the model is a good fit. Our hypothesis are always going to be, our H0 is going to be whatever the model is that we're testing is a good fit, and our H1 is always going to be that that model is not a good fit. And as you can see here, we've got quite a lot of these that we're going to have a look at. We're going to have a look at Poisson, binomial, normal, rectangular and uniform, exponential and predetermined models. And as with goodness of fit, if we have a look at our expected values, if any of those are less than 5, then we are going to have to pool some of our data. So the first one that we're going to have a look at is Poisson. So to perform a goodness of fit with a Poisson distribution, we must first find the probabilities using either PPD or PCD, and then multiply the probabilities by the number of observations that we have in the question to find out what the expected values are. As we only care about two things in this test, which is the number of observations and lambda, which remember is our mean and our variance, the degrees of freedom is the number of categories after pooling minus 2. However, if we've already been given the mean of the model, then because that is no longer something that is going to vary with our data, we would only do the number of groups after pooling minus 1 instead. So we have to be careful with that and pay attention to what we've been given in the question. We may have to work out the mean from the data provided, or we may have to test if the model uses a given mean is suitable. Okay, so the one where we're having to find the mean, we'd be doing minus 2. The one where we've been given a mean, we'd do minus 1. As Poisson has no upper limit, we have to ensure that the last interval reflects this. So we need to make sure that our last interval goes on forever. So, first example, the number of computer manufacturers per day is recorded for 260 days with the following results. Test the goodness of fit of the Poisson probability model. So here we haven't been told what the mean is, so that means that of our 2, we are looking at this first option here, which means that the degrees of freedom is going to be the number of groups after pooling minus 2. So to start off with though, we need to actually find out what the mean of these numbers are. So we're going to go into the stat function in our calculator, and just like we did in AS, we are going to put our outcomes into list 1. So 0, 1, 2, 3, 4, 5. We're going to put our frequencies into list 2, 77, 90, 55, 30, 5 and 3. Then we're going to go to calc, set. We've put our variable into list 1. We've put our frequencies into list 2. And then we're going to go to 1 var. So the mean of this distribution, our lambda, is 1.25. So we're actually seeing if x follows the Poisson distribution with a lambda of 1.25. Our H0 for this hypothesis test is going to be that the Poisson model is a good fit, and our H1 is going to be that the Poisson model is not a good fit. So as it said in the explanation above, we are now going to find our probabilities. So down the side here, I'm just going to put my categories. So we've got 0, 1, 2, 3, 4, 5. And as we said, we have to make sure that the fact that the Poisson distribution has no upper limit is reflected. So we're going to have greater than or equal to 6 as an extra category that we're adding on here. So then we're going to find our probabilities. So I'm going to go back into dist across Poisson, and we're going to go into PPD first. So for the first one, our x is 0, our lambda is 1.25 because we've just figured that out. And that gives me a probability of 0.28650479. Then going to change our x to 1, which gives me 0.358130099. Changing it to 2 gives us 0.223838187. Changing it to 3 gives me 0.09326328. Changing it to 4 gives me 0.02914477. Changing it to 5 gives me 0.007282. Now for this last category here, which I've added on, we actually need to go into PCD for this because it is a cumulative distribution, cumulative probability, sorry, that we're finding. The lower is going to be 6. The upper is going to be a really big positive number. Our lambda is still 1.25, which gives us 0.001831. Now, as it said before, we're going to times our probabilities by our number of observations. We've been told here that it was 260 days. We can double check that by just adding the observations together. So we've got 77 plus 90 plus 55 plus 30 plus 5 plus 3. And we can see that again, we end up with 260. So adding these numbers together here also gives us 260 if it's not given to us in the question. So our expected values are going to be 0.28650479 times 260, which gives us 74.491254. Then 0.358130099 times 260, which gives us 93.1140574. Then 0.22383187 times 260, which gives us 58.1962862, 0.09326328 times 260, which gives us 24.24845828. Then 0.02914477 times 260, which gives us 7.5776402. Then 0.0072862 times 260, which gives us 1.894412. And lastly, 0.001 18381 times 260, which gives us 0.477906. Now, as we said before, these are expected values, and we can see that we have some of them that are less than 5. Now, these last two here are less than 5, but also if I added those two expected values together, that would still give me a number that was less than 5. So actually, in order to make it so that none of my expected values are less than 5, I'm going to have to add all three of these categories together, meaning that this one is now going to become greater than or equal to 4. So I'm just going to go back in my calculator, dist across Poisson PCD, and I'm going to find the probability that we have greater than or equal to 4, which gives me 0.0382695, and then that gives me a new expected value of 0.0382695 times 260, which gives us 9.949953. And a way that we can check this is that if we added those three numbers here together, we should end up with the same value. Now remember that we still have these values here that we didn't have to pool. You don't have to rewrite them all out, you can just carry them across, but I am going to add, it's going to be a very small column now, a little observed column at the end. So we've got 77 for the first observed value here, then 90, then 55, then 30, and then these three here we are pooling together. So that's the 5 and the 3 and the group that I created going on forever, which had 0 to begin with, because I've just invented it so that we can have Poisson having no upper limit. So that means that that observed value is going to be 8. So back in the stat part of my calculator, I'm going to delete what I've already got in there. And then we are going to put our observed values into list 1. So we're going to have 77, 90, 55, 30 and 8, because we've pooled those ones together. Then our expected value is going to go into list 2, so 74.4912454, 93.1140574, then 58.1962862, then 24.248458, and then the last observed value, remember that, expected value, we put all these ones together and we got this value here, so that's going to be 9.949953. Then in our calculator we're going to go into test chi goodness of fit, and as you can see, my observed values, yes, I put them into list 1. My expected values, I put those into list 2, and then it's asking me for the degrees of freedom. So remember, we said that the degrees of freedom is going to be the number of groups after pooling, which in this case is 1, 2, 3, 4, 5. And because we had to calculate the mean from our data, we're going to take off 2. So that gives us a degrees of freedom of 3. So our chi-squared value is 2.11 to 3 significant figures. That is our test statistic. Our critical value we're going to get from our formula booklet, which is on page 20. So we're going, it doesn't give us a significance level, so we're going to use 5%. So we're going down from 0.95 across from 3, which gives us 7.815. as our critical value. And then just like we had for our chi-squared test in AS, as the test statistic is smaller than the critical value, that means that we accept H0 at a 5% significance level. There is insufficient evidence to suggest the Poisson model is not a good fit. Because remember that when we're writing our conclusions, we always write about H1. Our H1 here was that the model was not a good fit. So when we've wrote our conclusion here, we've said it's insufficient evidence to suggest that the Poisson model is not a good fit. So as I said before, we can also be asked a question where we're actually given the mean. So here we have Michelle believes that the Poisson model with a mean of 1.3 will fit the following data. So we've got some data here. Perform a hypothesis test at a 5% significance level to determine whether Michael is correct. So straight away we already know that we're using X follows the Poisson distribution with a mean of 1.3. Our H0 this time then is going to be that the Poisson model with mean 1.3 is a good fit. And H1 is going to be that the Poisson model with mean 1.3 is not a good fit. So when we are given the specific mean that we are wanting to test, we want to make sure that we are including that in our hypothesis. Then we're going to follow the same steps as we did before. So I'm going to put my data down by number of black cars down the side, not 1, 2, 3, 4, 5. And remember that we have to create a category for greater than or equal to 6. Then we're going to find our probabilities. So we're going to go into dist Poisson PPD to begin with. 0, 1.3 gives us a probability of 0.27253179. When we change that to 1, we get 0.35429133. When we change that to 2, we get 0.23028936. When we change that to 3, we get 0.099799205. When we change that to 4, we get 0.03243241. When we change that to 5, we get 0.0084324. Then we need to come out of that and go into PCD for our last one, which starts at 6, has no upper limit, and that gives us 0.0022306. Then to get our expected values, we need to times it by the number of observations that we had. So we need to add these numbers here together, which gives us 5 plus 6 plus 9 plus 4 plus 3 plus 1, which gives us 28. So then we need to multiply our probabilities by 28. So we're going to have 0.27253179 times 28, which gives us 7.63089012. 0.35429133 times 28, which gives us 9.92015724. Then 0.23028936 times 28, which gives us 6.44810208. Then 0.09979205 times 28, which gives us 2.79417774. Then 0.03243241 times 28, which gives us 0.90810748. Then 0.0084324 times 28, which gives us 0.236172, and lastly 0.0022306 times 28, which gives us 0.062458. Now, just as we had last time, we are going to have to do some pooling, and this time if we added these last four together, that still would not be enough to get our expected value above 5. Okay, so that means that we are going to have to pool all of these groups here together, which means that we're going to have greater than or equal to 2. So then back into dist across Poisson PCD. We're starting at 2, we're going up to a really big large positive number, and that gives us 0.3731767 as our new expected value. Our new probability. To get our new expected value, we're going to have to times that by 28, which gives us 0.37317 times 28, which gives us 10.44895236. Just as before, I'm just going to put my observed values just down this side. So my observed are going to be 5, 6, and then we're pooling all these last groups here together. So we're going to have 9, 4, 3, 1 all being pooled together. Sorry, it's just going a little bit slow at the minute. Whoop. Which then gives me so 9, 4, 3 and 1, which gives me 17. So in my calculator, I'm going to delete what I've got in there. My observed values are 5, 6 and 17. My expected values are 7.63089012, 9.92015724, and then 10.44895236. Then remember that we're going to calc test, chi, goodness of fit. And this time, our degrees of freedom, we've got 3 groups left after pooling. We've got this one here, and this one here, and then our pooled one here. So we've got 3 groups, but because we were already given the mean in the question, that means that we're only going to take 1 off of that for our degrees of freedom. So our degrees of freedom is going to be 2. That gives me a chi-squared value of 6.56, which is our test statistic. The critical value, getting it from page 20 in our formula booklet. At a 5% significance level, so looking down from 0.95, across from 2, gives me 5.991. So then as the test statistic is bigger than the critical value, this time we would end up rejecting H0. So at a 5% significance level, there is sufficient evidence to suggest the Poisson model with mean 1.3 is not a good fit. And because we've been told what mean to use, make sure that in your conclusion you are saying that a Poisson model with a mean of 1.3 is not a good fit, because maybe a Poisson model where we actually find the mean from the data would be a good fit, so we need to be specific in our conclusions. So now I'd like you to go on to the Now You tries. Thank you very much for watching.